So something you may have seen before, but in probably never been put together, all the different concepts, what are called polynomials. And so basically polynomials are anything that has x to the power of something. So I'll show you what the form of it is. So it's the function of x, and you're going to have some sort of number plus another number times x plus another number times x squared, and we call these coefficients here whatever we want, but in this case a1, a0 to all the way up. And so you can see that you can keep going with this x to the 3 plus a 4x to the 4, and it just keeps going and keeps going. And the general form of it is we say it's a to a number n times x to the power n. And so this is kind of like the general form of a polynomial. So let's look at what a polynomial of 0th order is. 0th order. So that is basically chopping it off here, and that's just a number. So that's really quite simple. It's just 0 is going to be equal to a0, which is a constant. Okay, so let's go to the second one. N is equal to 1. And so we chop it off here. And so it's f of x, and this is the first one. Number 1 is a0 plus a1 x. And this is just a linear function. More commonly you've seen this as y equals mx plus c. And we can see that y in this case is the f of x, is the function. That's because we plot it. We're plotting f of x by the function mx plus c. We'll see that c is actually a0, and we see that m is a1. And so we can start to think about this here as potentially being kind of like a y-intercept. We can think of a1 as being the slope of the line, because we know that usually when we describe a line using y equals mx plus c, then where it intercepts the y-axis is our c value, and the slope of this line, m, which is equal to the rise over the run, is going to be equal to our a1 value. So this tells us the slope, and that tells us the y-intercept. And these are really quite easy to solve. So what you usually do is you take 2 points, you work out the rise, so it's going to be y1, y2, so you'll go y2 minus y1, and then you're going to have x1, x2, and you subtract them, and you get the rise over the run, and that gives us the m value. And then we can substitute that into the equation, and we can just pick any point along the line, and we can solve for c. So that's nice and easy. So that's a linear function. So a polynomial of first order is just a line, or a linear function. So what is n is equal to 2? So these are of the form f of x is equal to a0 plus a1x plus a2x squared. And you're probably most used to, this is a parabolic function, you're probably most used to no linear term, and so it's just going to be a parabola, and then this here is basically the offset, you know, where it intercepts the y-axis. And this is a quadratic function, and we are used to seeing it in this form: ax squared plus bx plus c, and we usually equate equate that to 0 if we're going to solve this, and we know that so when y is equal to 0, that is our roots of the quadratic. So we can think of a quadratic as being just a parabola, and when y is equal to 0, it's at the point where the line crosses the x-axis. And so when y is equal to 0, then we can say that then we can solve this and find the values of x that give us these what's called the roots of the quadratic. And the equation for this is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. And so we can just put in the values and we can find the roots. Now there's something quite useful about this top bit here, and we'll come back to it a little bit later, but basically it's called the discriminant, and basically if this number is greater than 0, so if it's a positive number, we're going to have 2 roots. And if this is equal to 0, then we'll get 2 equal roots. And so this 2 real roots is this case here. If we have it equal to 0, then we're going to get this case here where it only intercepts it at 1 point. So you're going to have 2, the roots are going to be the same. You're going to have 2 equal roots. And if you have the discriminant as less than 0, so a negative number, then it's floating up here and it never crosses the x-axis. And so these ones here only have what are called complex roots, and we'll come back to that when we introduce a new number, a new form of maths, a new object called the imaginary number. We'll come back to that next week. So what applications are there for this? Well, often when we describe interactions with molecules, we try and approximate the interactions using polynomials, because they're much easier to deal with than the complicated functions that we deal with inside of molecules. So an example of this is if we look at two molecules here, and we say that that this is the radius between the two atoms, and so we're going to plot the radius as a function of energy. So as we come closer and closer together, these are coming closer and closer together, they're all the way out here, over here, they start to attract, they start to share electrons. Let's say this is a covalent bond. But at some point they're going to get too close, and the nuclei are going to start repelling because they're positive, and we're going to get it going all the way up very, very fast. And this here is what is called our bond length. And this is a balance between a function which is attractive and a function which is repulsive. And so that's how we get this overall curve. And basically molecules vibrate. They vibrate back and forth. And so basically this is kind of like if you were to put a marble here, you'd expect the marble to kind of roll back and forth and back and forth, and if there was no friction it would continue to kind of vibrate. You can think about it in a certain direction along this what we call a potential. And so the molecules kind of vibrate inside of this well, this energy well, and we can basically represent this by a parabola. and as long as the molecules don't have more energy than a set amount, it's a pretty good approximation. But as soon as the atoms have a certain amount of energy that is greater than this, you start to see that there is a deviation from the simple model. But you'll see that, it's describing something as a0 plus a1x plus a2x squared, that's much easier than the functions we have to put together in order to describe this complex shape of this balance between the repulsion and the attraction. And so one application of polynomials is to approximate quite complicated functions. We use it all the time in chemistry and also in physics to describe systems. And the more polynomials we add, we often will actually describe more phenomenon. So for example, if you were to add a third polynomial, then you'd start to describe this petering off here. So you could actually start to describe the fact that this is not symmetrical, and that's what's called an anharmonic oscillator. So you can start to see that by adding more and more terms, you can better approximate the function, and that's why polynomials are very useful, and we'll later use them in order to define many other things.